Hello, Math 101 students. Welcome to the first lesson of the course. In this lesson, we're going to talk about antiderivatives. Our goal for today is to study antiderivatives. Finding the antiderivative of a function is pretty easy if you understand how to find the derivative. For example, if you have a function looks like this, x squared over 2, take the derivative of this function gives you 2x over 2, which is equal to just x. Now, finding the antiderivative is exactly the same process except that we're going back to the original. For example, the antiderivative of x is actually this guy, which is x squared over 2. But one thing that you have to remember for the future is that just add a constant at the end. This is the antiderivative of this function x. If you understood so far, let's jump right into the examples. I'm going to call this portion of the column to be original function. So let's construct a table. Let's say this time I have original function to be x cubed over 3. Take the derivative of x cubed over 3 gives you. So take the derivative of this guy and let's define this function to be f of x. Then it becomes 3x squared over 3 becomes just x squared. Now, if you take the antiderivative of this guy, we're not going to use little f as the function. This time, antiderivative is written as big F. So the big F, which is the antiderivative of this little f, is equal to this original function, which is x cubed over 3 plus the constant c. Please do not forget about the c. The reason is, if you take the derivative of x cubed over 3 plus c, you believe that it's going to go back to x squared plus what? The derivative of any constant is equal to 0. That's why we must have constant, because this is the most general expression of antiderivative of this function here. Okay, let's try more examples. Please take a look at our slides. Suppose our original function is x to the power of 4 over 4. Then the derivative of this function is little f of x is equal to 4x cubed over 4 becomes x cubed. So that the antiderivative of this little f of x is equal to capital F equals this original function x to the power of 4 over 4 plus c. And you need to have c because this is the most general expression of the antiderivative of this function. Now, did you guys notice the pattern? If your original function has power 2, then the antiderivative has one more bigger than the original power, say 3. And then copy and paste the original power at the bottom. Same for this guy. If the original power is 3, the new power is one more than 3, which is 4, and then copy and paste the new power at the bottom. So here's the question. Suppose I give you f of x to be x to the power of n, like this. Then what is the antiderivative of this x to the power of n? If you said x to the power of n plus 1 divided by n plus 1 plus c, then you're correct. So the original function for this derivative was this. So this is the power rule for integrals or antiderivatives for now. So let's put a big box around this. Okay, please use this. So far, we work with polynomial functions. How about we have trigonometric functions like sine or cosine or tangent? So let's say our original function is sine. Then the derivative of sine x is cosine. Now, what's the antiderivative of cosine? The antiderivative of cosine is sine x plus c. Similarly, if the original function is cosine, then the derivative of cosine is negative sine x. And therefore, the antiderivative of negative sine x is this guy, which is positive cosine x plus c. Now, what if we didn't have negative sign here? Suppose we had sine x and take the integral or take the antiderivative of this guy. Antiderivative of sine x is not positive. It's actually negative cosine x. Please remember. It's kind of opposite from the derivative. Before, when we take the derivative of cosine x, we get the negative sine x. Do you understand? However, this time, when you take antiderivative of sine x, then it must be negative cosine x. But because we had negative sign here, negative makes it positive. So that's why it's positive cosine x plus c. So please remember this rule as well. Now, tangent is easier because we don't have to worry about the signs. Suppose we have tangent x. Then the derivative of tangent x is secant square x. And then the antiderivative of secant square x is tangent x plus c. Before I do more examples, I'd like to briefly mention the notations for antiderivatives. Quite often, we use capital F for antiderivative of little f. In Math 101 class here, we use another way of writing antiderivative, and you're going to see this notation a lot in the future. It's called indefinite integrals, and it looks like this kind of symbol. So the capital F can be rewritten as integral of little f of x dx. This kind of notation is called indefinite integrals. So let's write it down. Use capital F of x can be written as integral little f dx. And we're going to use this a lot. So why don't we just practice from now on? Instead of writing big F, let's write down integral. Let's continue finding the antiderivative of a function here. This time, I didn't even write down antiderivatives because by now, you all understand that integral of f of x dx means antiderivative of this function here. Anyways, take the derivative of this one. Do you remember from Math 100? It becomes negative cosecant square x. And then the antiderivative of f of x dx is equal to, we're going back to the original function here, so it becomes cotangent x plus c. Now, let's suppose we have secant x. Then the derivative of secant x is secant x tangent x. And then the antiderivative of this function is actually going back to this guy plus c. So I'm just going to use capital F actually because I'm running out of space. So capital F, which is the antiderivative of this guy, is secant x plus c. Okay. Now, from Math 100, if you have ln of x, then take the derivative of ln x becomes 1 over x, right? How about we take the antiderivative of this guy? Antiderivative of 1 over x is going back to ln of x plus c. But everyone, I'm going to use absolute value here. I do not want to confuse anyone here, so if you trust my words, you can just memorize that the antiderivative of 1 over x is actually equal to ln of absolute value of x. And you can skip this part. For those of you who want to know why this is absolute value of x, I'm going to explain with the left-hand side screen here. Suppose you see the original function, ln of negative x here? Well, of course, in order to make this function well defined, x must be negative so that you have a positive number. So ln of negative x and take the derivative and you get 1 over negative x times by negative 1 by the chain rule. Well, negative negative makes it positive. Did you notice that we have 1 over x? Hence, integral of 1 over x is equal to the original function ln of negative x plus c. And of course, if you have a ln of x with x is positive, then the derivative of ln of x is 1 over x, right? And the integral of 1 over x is ln of x plus c. So altogether, everyone, ln of x, we have ln of negative x. We have two cases here. One positive case and then negative case. Altogether, we have ln of absolute value of x plus c. So long story short, antiderivative of 1 over x is equal to ln of absolute value of x plus c. Make sense? Okay, let's move on to the next example, which is e to the x. I love this example because e to the x is the most simplest derivative and antiderivative in the world. The reason is, if you treat this as original function, then the derivative of e to the x is e to the x, and the antiderivative of e to the x is, we are going back to the original, plus c. Okay, here's the last one. Suppose the original function is inverse tangent of x. Sometimes people call it arctangent. This or this, same thing, okay? Take the derivative of inverse tangent. What do you get? You get 1 over 1 plus x squared. Do you understand? Now, take the antiderivative of 1 over 1 plus x squared. You're going back to inverse tangent. Okay, that's the end of many examples. Okay, move on to the next concept. Now, let's write down the proper definition of antiderivative here. So, let's write it down together. A function, capital F, is called an antiderivative of little f of x if it satisfies the following equation, which is the derivative of the capital F becomes the little f. So as long as the derivative of capital F comes back to the original function, then we can call it an antiderivative of little f. Please note, now this reveals the secret of having plus c at the end. Because if you notice that the derivative of e to the x plus 1 becomes e to the x. The derivative of e to the x plus 2 becomes e to the x, and so on. So this brings us the following question. The question is, why do we always add plus c at the end for the derivative, for the antiderivative? Suppose our little f of x is x squared. And then by now, you know that the antiderivative of x squared is big F equals x cubed over 3 plus, you know that it's a c, but as an example, let's put 1 for now, okay? Then, if you differentiate this capital F, what happens? Let's find out the derivative of this guy. Then, the derivative of capital F becomes 3x squared over 3 plus 0. Because the derivative of 1 is 0. Do you understand? So the derivative of capital F becomes little f. Do you agree? So that's why this satisfies the definition of antiderivative. Capital F prime becomes little f. So let's try one more time. Suppose the antiderivative becomes x cubed over 3 plus 2. Then surely the derivative becomes x squared as well because the derivative of constant is equal to 0. So please look at the left-hand side screen here. If you have x cubed over 3 plus 1, or plus 2, or plus 3, all of these functions' derivative becomes x squared, right? And all of these functions satisfy the definition of antiderivative. Therefore, the most general expression of the antiderivative is, this is the reason why we need to use C, because the derivative of any constant is 0 and going back to the original little f of x. We call this kind of expression as the most general antiderivative of little f of x. So please write it down. Okay, whenever we talk about most general antiderivative of f of x, that means think about C at the end. All right, everyone, let's try this example. We're gonna find the most general antiderivative of these functions. Let's try this easy function first. We have y equals x minus 3. The antiderivative of this function, our plan is to do it term by term. For example, the antiderivative of x becomes x squared over 2. Now, the antiderivative of 3 becomes 3x, right? Of course, we have minus sign in between, so let's write down the minus sign. So this is the antiderivative term by term. So altogether, the most general antiderivative of this function is big F of x equals x squared over 2 minus 3x plus c. And that's the end of part A. Part B, we have exactly the same plan. We're going to find antiderivative term by term. 1/2 x squared, its antiderivative becomes 1/2 times by x cubed over 3, and then minus. The antiderivative of 2x becomes 2 times x squared over 2, like so. And then the antiderivative of 6 becomes 6x. So altogether, the most general antiderivative can be written as big F of x equals 1 times x cubed becomes x cubed over 2 times by 3 becomes 6 minus, here 2 and 2 cancel with each other, so it becomes x squared plus 6x plus c. Okay, that's the end of finding the most general antiderivative of these functions. If you have any questions, please let me know by email. Before we try the next example, let's try some warm-up questions. The first warm-up question is, let's say you have a fraction like this. You know that you can split this one fraction into multiple fractions like this. A over d plus b over d minus c over d. So this method is very useful when finding the antiderivative because we can use the power rule if you split the fraction into term by term like this. Next, suppose you have a square root of x. You know, by using the exponent law, root x becomes x to the power of 1/2, right? So if you take the antiderivative of this guy, it becomes x to the power of, antiderivative means you have to add 1 to the original power. So 1/2 plus 1 becomes 3 over 2. And then you know that it must be copy and paste the new exponent at the bottom like this, like that. And then please focus on this number at the bottom. This 2, you can flip it to the numerator. So this expression simplifies to like this. If you understood so far, then you're ready to tackle the next examples. Here's the next example. Find the most general antiderivative of this function and this function here. From the warm-up question above, we can split this one fraction into multiple parts. So we can also do that for this function as well. In other words, x to the power of 5 over x to the power of 4, and so on. For this guy, we can change the square root expression as well, like this, like that. Then we can also change this, looks like this, 2 times 1 over x. For this first part of the function, you can simplify this, and looks like f of x becomes x minus 1 plus 2 over x. And then this one, you can just, this function is ready to take the antiderivative. So just like before, we're going to find the antiderivative term by term, like this. Antiderivative of x becomes x squared over 2, like so. And then the antiderivative of 1 becomes just x. And then we have a minus sign, so let's put the minus sign here. And then the antiderivative of 2 over x, you need to be a little bit careful. Do you remember? Right here, the antiderivative of 1 over x becomes ln of absolute value of x plus c. Do you remember? So we're going to use this. If you have 2 over x as the original function, then antiderivative becomes 2 times ln of absolute value of x. So the antiderivative of 2 over x becomes 2 times ln of absolute value of x plus c, like this. Now, the antiderivative of 1 becomes x, and then the antiderivative of x to the power of 1/2, well, we already did this in earlier warm-up question. X to the power of 1/2, antiderivative becomes, looks like this. And if you simplify by moving the 2 to the numerator, then I get 2 times x to the power of 3 over 2 all over 3. So like this. And then 2 times 1 over x becomes exactly same as this guy, which is plus c at the end. Don't forget about this. Okay, that's the end of this example. Now, to check your understanding of the subject, I'd like to give you a your turn question, which is this. Find the most general antiderivative of 3 times square root of x minus 2 times cube root of x. Well, there's a solution to the left-hand side screen. You can read my solutions and check if it seems reasonable for you. If not, please let me know by email again. Okay, that's the end of part 1, and I'm gonna see you soon with part number 2. Part number 2, solving initial value problems using antiderivatives. Now, I'm hoping that you understand that if there is a f prime, which is the first derivative of f of x, and if you find the antiderivative, then this f prime becomes the original function f of x, right? So the first prime means the number of anti-differentiation that you have to take in order to get the original function f of x. So for instance, if you have f double prime, if you take the antiderivative of this guy once, I'm just going to call it AD, means antiderivative, then you do not get the original function f of x. In fact, you'll get f prime, not the f. So in order to get the f, you have to apply the anti-differentiation once more. Then you will get f of x, like so. So technically, the number of primes or the order of the derivative tells you how many times you have to apply the anti-differentiation in order to get the original function f of x. But please remember, each time you take the antiderivative, you have to add what? You have to add c, but because you used the c earlier here, if you take the antiderivative here, you cannot use the same variable c. Instead of adding c here, you have to add the new variable, which is add d or something. Do you understand? So our goal is to understand this warm-up problem first and then solve initial value problems.
If you understood everything so far, then you're ready to tackle the next example. All right, everyone, let's try this example. Currently, we have f prime of x equals 2x cubed minus 3x to the power of 4. By the way, do you know why this kind of setup is called initial value problem? It's because the question has kindly given us the initial value, which is when the x is 0, the y value is 1. Well, think about this, everyone. If you take the most general antiderivative of this guy, you're gonna need the variable c at the end. Do you agree? But having c means it's indefinite solution to this differential equation. Having this initial value actually makes you solve the unknown c value. If you don't understand what I'm talking about right now, it's okay. I'm gonna write down the solutions and then you will understand at the end. Stay tuned. The first step is to find out the antiderivative, or actually the most general antiderivative of this equation here. So we're gonna find antiderivative term by term. So 2 times x cubed becomes 2 times x to the power of 4 over 4, like this. And then 3 times x to the power of 4 becomes 3 times x to the power of 5 over 5, like so. And then we have minus sign, so you should have minus sign here as well, like this. Okay, anyways, f prime, and after applying the anti-differentiation, then it becomes f of x. So I'm just going to rewrite this f prime as f of x like this, and then simplify the expression a little bit, like this. Then the f of x becomes x to the power of 4 over 2 minus 3 times x to the power of 5 over 5. Of course, this is the most general antiderivative, so we have to add c right now. In order to find out this unknown c, we need to use this initial value, which is f of 0 equal to 1. Did you notice that? This 0 means when x is equal to 0, this 1 means y value is equal to 1. So we know x is 0, y equal to 1, plug it in here. 0 over non-zero minus 0 times anything is 0. So what does it mean, everyone? It means the constant c must be equal to 1 in this case. So this solves the initial value problem for this guy. In other words, our f of x was hidden to be. Okay, that's the end of this example. Let's try another one. Okay, here's the last example for this module 1-1. Find the function f of x if the second derivative equals 4 over 3 x to the power of 1/3. Did you notice that we have two informations on initial values? The reason is, how many primes do you see? It's double prime. That means we need to take the antidifferentiation twice. So for example, like this. Our goal is to apply the antidifferentiation on f double prime to make it f prime. From f prime to make it f. But please be careful, everyone. Whenever you try to do this, don't forget that you need to add constants like plus c for this guy, and then plus the different constant like d for this guy. So at the end, how many unknowns do you see? C and D are the unknowns for the function f. Okay, we need these information to solve for D and C. Okay, all right, let's try this. F double prime is 4 over 3 times x to the power of 1/3. So like this, right? Suppose you apply the antidifferentiation once. Then 4 over 3 act like the constant, like this, times by x to the power of 1/3 becomes x to the power of 1/3 plus 1, which is 4 over 3, like this. And then, of course, copy and paste this new power at the bottom, which is 4 over 3. Makes sense. Simplify this a little bit by moving the most bottom. Okay, if you see this, the most bottom 3 flips to the numerator and it becomes 3x to the power of 4 over 3 over 4. And then the good news we have is that we can cancel 4 here, and 3. So it looks much nicer expression. We have just found out f prime from f double prime. So our f prime of x is equal to x to the power of 4 over 3 plus, please don't forget about the constant c at the end. So plus c like this. Our goal is to find out the f. In other words, you need to take the anti-differentiation once more, and please do not forget about d at the end. So, like so. F of x is equal to the antiderivative of x to the power of 4/3 becomes x to the power of 7 over 3, and then the new power becomes the denominator. However, I would like to simplify a little bit so that it looks like 3 over 7. Please look at the left-hand side screen. So, like that. And then the antiderivative of c becomes cx. However, please do not forget about the constant d, so we must add the d over here. Now you realize that, oh, to find out these unknown variables, we need to use these initial value informations. F of 0 equal to 1 is one of them. F of 1 equal to 3 is another one. So using f of 0 equal to 1, we get the y value becomes 1 here, and then the x becomes the 0. So 0 plus 0 plus d becomes, the secret for d becomes 1. Now, so far, our f of x looks like 3 over 7 x to the power of 7 over 3 plus c times by x plus d is equal to 1. Now, in order to find out the unknown c, we have to use the last piece of information here. F of 1 equal to 3. That means the y value is equal to 3 here, and then the x value is equal to 1. So the y value is 3, and then the x value is 1 here, 1 here. And then solving for c, we get move the 1 to the other side becomes negative 1. And then move 3 over 7 to the other side becomes negative 3 over 7. And of course, originally 3 was positive, so let's put plus sign there. Then this must be equal to c. Doing some algebra, and you can also check my work from the left-hand side screen here. C becomes 11 over 7. So altogether, our function f of x becomes 3 over 7 x to the power of 7 over 3 plus 11 over 7 times by x plus 1. Okay, thank you everyone. That's the end of module 1-1.